Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next session of System Programming with Linux. The title of today's session is Synchronization Among Threads. Before going through this session, I will request you all to please go through the video lecture number 23 on multi-threaded programming. If you are not comfortable with programming the POSIX threads. Well, this slide shows the agenda for today's session. And before I proceed, let me have a quick recap of POSIX threads. And for that, let me move on to the Linux terminal. Well, dear students, on most of Linux distributions, you will come across two famous thread implementations. The older one is the Linux threads and the newer one is the NPTL threads, native POSIX threads library. And to discover the thread implementation on your system, you can use the command getconf gnu _lib pthread _version, and it will tell you the NPTL version or maybe the Linux thread version on your machine. On most of the systems, the man pages for thread functions are normally not installed. So you can install them by sudo apt-get install glibc-doc, or you may use apt-get install man pages -POSIX. So this is already installed and the newest version. So after you have installed the man pages, the first page I want you to read is man pthreads, and it is a very informative page, shows you a lot of information like the process-wide attributes, the thread specific attributes, and it gives you information about the IDs, information about the Linux threads, information about the NPTL threads, and so on. Okay. Well, in the session 23 of threads, we discussed some basic thread functions like man pthread _create, that is used to create a thread, is passed 4 arguments. In the first argument, we get the thread ID. The second argument is a pointer to the type of the thread attribute, and you can keep a null over here, or you can pass a pthread attribute t type of object over here. And this is a function pointer to the thread function, which is passed one argument of void pointer and returns exactly void pointer. And fourth argument is of course the argument you want to pass to the thread function. Fine, do go through this man page, do go through the man page of pthread _exit, that is used to terminate the calling thread. To go through the man page of pthread join, and which is similar to wait PID and used by peer thread to wait for the termination of another thread, and of course receiving its exit value. And we have also seen the usage of pthread self that displays thread IDs, and thread IDs you get via pthread self are actually maintained by thread implementation and are unique within the process only. On the contrary, if you use the function get TID, you again get the thread ID, but this time the thread ID you get is assigned by the kernel, which is similar to the process IDs, and these are unique across the system. We also discussed different attributes of threads, particularly its detached state, pthread, I don't know why this Q is coming, pthread _attr_init. This function is used to initialize the attribute object with the default settings, and later we have used pthread attr underscore, yes, this setters functions, and these setter functions, there are a lot of setter functions, and we have used this set detached trait to create a detachable thread. Okay, so let me show you the program that we discussed in the previous session of multi-threading. And we created a program that creates two child threads, and each thread counts the number of characters in a file. I think that was rv2.c. Well, yes, this was the one. This program was passed two command line arguments, which were file names, and it creates two threads and pass those two file names to that thread, and then join those two threads. And those two thread functions count the number of characters in the files and return those values in these two variables, and those two variables are displayed by main. Pretty fine. And this is the thread function. We discussed it in detail. Okay, let me compile this program rv2.c. Make it your habit to compile your code with -d underscore reentrant flag. Let me pass two files name to this program, small.txt and long.txt, and let me confirm it using wc as well. Okay, so you see that it's great. Small text.txt file has 7973 characters, and the long file has 18258 characters. I think enough of recap. Let's fall back to the slides. Okay, well, dear students, I am sure we all have studied the concept of synchronization, race condition, mutual exclusion, and critical section in our operating system concept course. However, let me do a bit of dusting of this as well. Excuse me. Well, in computer science, synchronization refers to the relationships among events, for example, before, during, or after. There are two constraints of synchronization. The first is serialization, and that is event A must happen before event B. The second is mutual exclusion, that is event A and B must not happen at the same time. In multi-threaded programs, the programmer has no control over when a thread runs, as the scheduler makes this decision. So concurrent access to shared data may result in data inconsistency. And we need to apply some concurrency control mechanisms using which multiple threads can access shared data without any conflict. Let us see an example of data corruption. Consider a bank account having a balance of ₹100. A deposit process or deposit thread deposit ₹25, thus updating the balance of that account to ₹125. A withdrawal process runs with a withdrawal amount of ₹10 and thus updating the balance of that account to ₹115. The instruction inside the deposit and the withdrawal process that update the balance variable can be written in assembly as shown below. Well, in the deposit process, you can see it moves the balance amount to the register R1, then it adds the deposit amount with the contents of R1, and then finally it moves the contents of R1 to balance. And similarly, we can see over here we have a subtract. Well, dear students, these are the three lines in the deposit process which makes up the critical section, and similarly these are the three lines in the withdrawal process that makes up the critical section. Because this is a piece of code in which these two threads are updating that shared data. This is what the definition of critical section is. And the critical section problem is if multiple threads try to execute their critical sections simultaneously, we need to execute them one by one concurrently. Let's see if they are not executed one by one, rather they get overlapped. If they get overlapped something like this, that is, this instruction execute, then this, and then this and this, that is they are not overlapping, we get the correct answer, that is rupees 115. But if they get overlapped something like this, we get the balance of 90 instead of 115. And if they get overlapped like this, we get a balance of 125 instead of 115. Over here you see that the withdrawal process is the last to finish and we get the balance of 90. And over here you see that the deposit process finishes last and we get a balance of 125. So this is what is known as a race condition, which is a situation where multiple threads are reading or writing some shared data concurrently, and the final value of the data depends on which process or thread finishes last. So this is, I think, the concept we have seen in the operating system concepts course. I have brushed it up. And let me now move on to the Linux terminal and see some sample codes that will show the proof of this concept. That is, there will be a critical section problem and a race condition and the results will not be correct. So let's move over here. Let me clear screen. Let me show you sample code race1.c. Well, in this program you can see we have a global variable balance right now over here, that is initialized with the value of 0. The main thread creates two threads. One will execute the increment function and the other thread will execute the decrement function. The main thread then joins the other two threads. If I fall down over here, this increment function actually increments the balance variable about 100 million times, while this decrement function decrements the balance variable the same amount of time, that is 100 million times. These two functions are executed concurrently by the two threads, and finally this main thread displays the value of balance, and which I think should be 0, and you all must be thinking that it should be 0. Let's see that. Let me compile this race1.c, link it with the pthread library. Let me execute it. Okay, so we have some negative value, some positive value, and again some negative value. Note the different output each time the program is run. This is because the race condition between the two threads calling the increment and the decrement function. And this is because the balance variable is a global variable that is being shared between the two threads. Let's see another example. race2.c. Okay. Well, this program also has a global variable word count initialized with the value of 0. The main thread creates, the main thread receives two command line arguments, which are actually the file names, and it needs to pass these file names to the thread functions. The main thread creates two threads, pass the file names to those threads, and then finally joins them. And both the threads note that both the threads are calling the same function, that is f1. Well, this thread function f1 that receives the file name, opens it and counts the number of characters in that file and update the global variable word count. Both the threads call the same function and update the same global variable. Finally, the main function displays the sum of the characters in both the files. Let me compile this program now, race2.c. Let me run it on small file and long file again this time, and this time it is giving the sum of the two the characters of the two files. And let me run wc as well on small file and long file, and you see the actual program wc is giving me the total number of characters in the two files 26231, while this is giving a different answer. Let me run it again. Let me run it again. Let me run it again. You see, every time I run it, it gives me different results. This is because of the race condition. Let me fall back to the slides again. Okay, and let me discuss the concept of data sharing among threads. Well, dear students, normally modifying an object requires several steps. While these steps are being carried out, the object is typically not in a well-formed state. If another thread tries to access the object during that time, it will likely get a corrupt information, and the entire program might have undefined behavior afterwards. So the question is, what data is shared among the threads? Well, remember, global data and static local data. The case of static local data is only significant if two or more threads execute the function containing that static local variable at the same time. Second is dynamically allocated data in heap. The third is data members of a class object that has two or more of its member functions called by different threads at the same time. And what data is not shared? Local variables are not shared, and function parameters are of course also not shared. Let me show you a program for a proof of concept. Clear screen. Let me show vim share data.c. Okay. So, this PTR is a global variable and is referenced by all three threads. That is the main thread over here and thread function as well over here. So this is shared among all these three threads. Well, this message MSG is an array of character pointers and it is local to main thread. But over here you can see that it is being assigned to PTR. So this is also shared among all the three threads. As far as this I is concerned, this is a loop variable and this is local to main thread only. It is not being shared by the other two threads. Okay, fine. If we come on to the thread function, here we have a local variable but being static. Inside the thread function, this is shared by both the threads. Both the threads will be accessing this variable. So this is shared among T1 and T2. And this my ID is local to each thread, T1 and T2. Let me run this program. Shared data.c -lp thread. Okay, let me show the code of this program as well for a bit of understanding. Okay, so this is the line which is being displayed over here. Note the behavior of the static variable. So dear students, you should have a very clear idea as to what all data is shared among threads if you want to write good concurrent programs. Let me talk about the thread safety as well. Okay, so there are two flavors of functions you must remember and you will come across while coding the concurrent programs, and they are thread safe functions and the reentrant functions. A thread safe function can be called simultaneously from multiple threads, even when the invocation uses shared data. This is because each thread accesses shared data using some concurrency control mechanism. So they are very good functions. On the contrary, a reentrant function can also be called simultaneously from multiple threads, but only if each invocation uses its own data. Therefore, we can say that a thread safe function is always reentrant, but a reentrant function is not always thread safe. There are a lot of thread unsafe functions which I have listed over here. There are more as of such category, and you will come across the reentrant version of these thread unsafe functions. That is one of the reasons I normally recommend that you should compile your code with -d_reentrant defined, so that the reentrant version of these functions are used by the compiler. These are the four classes of thread unsafe functions. The first class is the one in which you fail to protect shared variables. Second class is relying on persistent state across invocation. Third is returning a pointer to a static variable. And last is calling a thread unsafe function from your thread function. Okay, I think now we are well equipped to understand the solution of the critical section problem and the race condition. And for that, let's talk about what is mutex. Well, dear students, a mutex is a mutual exclusion device and is useful for protecting shared data structures from concurrent modifications and implementing critical sections. A mutex has two possible states, unlocked and locked. It can never be owned by two different threads simultaneously. A thread attempting to lock a mutex that is already locked by another thread is suspended until the owner thread unlocks the mutex. And finally, Linux guarantees that the race condition will not occur among threads attempting to lock a mutex at the same time. These are the steps that you should follow to use a mutex. First of all, you should create and initialize a mutex variable. When you have done that, several threads may attempt to lock the mutex, but only one thread will succeed, and that thread owns the mutex. The owner thread carries out operations on the shared data and finally unlocks the mutex. And later another thread acquires the mutex and repeats the process. And once you are done with your logic, you finally destroy the mutex. Well, whenever you are creating the mutex, there are two ways to initialize it. The first is if you say that you want to initialize the mutex with default attributes, you can define it statically. Pthread mutex tmut is equal to pthread mutex initializer. This is a constant you can use. And secondly, you can use pthread mutex init function, in which you pass the mutex pointer as well as the mutex attribute as a second argument. And even over here, if you are interested in the default attributes, you can place a null over here. You can see the main page of this function for details. Well, after you have created and initialized the mutex, you can call the lock, unlock, try lock, and the destroy functions. Well, remember the lock call will lock the pthread mutex object referenced by this mptr. And if the mutex is already locked, the behavior depends on the type of the mutex. Well, this unlock call release the mutex object. The manner in which a mutex is released is again dependent on the attribute of the mutex. Finally, this destroy will destroy it, and try lock will similar to lock, except that if the mutex object is currently locked, the call returns immediately with an error code, and that is EBZ. Okay, you must ensure these points to avoid deadlocks while using the mutex. And let me move on to the terminal again and see how we can resolve the critical section problems that we have seen in the previous example. Clear screen, and let me vim solution race1.c. This is the same piece of code where two threads increment and decrement global variable 100 million times, and finally the main thread displays the value of the balance variable as shown in this line. The value of balance variable is balance. Okay, over here if you see I have created a global variable pthread mutex t. Let me show you that. Yes, I have created a pthread mutex underscore t type of variable, and I have initialized it statically with the constant pthread mutex initializer. And I have used this variable in the thread function. Inside the thread function, I have identified the critical section, and over here the critical section is this, where this thread function is updating this global variable, and over here the critical section is this, where this thread is decrementing this global variable. So above and below the critical section, I have sandwiched the critical section with the lock and the unlock function calls. And before entering the critical section, the thread is locking this mutex, and after exiting from the critical section, it is calling the unlock function. And same is happening over here as well. Let us compile and run this program now and see if the race condition still exists or not. GCC solution race1.c -lp thread. This time the program may take more time to execute, as many times a context switch may occur while a thread is inside the critical section and the other thread spins for its time quantum. But rest assured, all the time the result will always be correct, and that is 0. So that is great. Let us see the other program as well, the character counter program, which counts the characters in 2 files. Solution raise2.c. Okay, so here again the word count is 0, the global variable, the pthread mutex underscore t. Well, this time instead of statically initializing the mutex variable, I have used dynamic initialization using pthread mutex init function. Note the second argument. The first argument is of course a pointer to this pthread mutex t variable, and the second argument I have placed a null, as I am using the default mutex type, which is the fast mutex. Rest of the code is same, and if I fall over here inside the thread function, you can see I am sandwiching this critical section line inside the lock and unlock function. That is great. Let me compile this program now. Solution raise2.c. Oops, let me link it. ./a.out. I need to give the name of the file small and long, and let me use WC as well on small and long, and you see 26231, the result will always be correct, and the result will be same no matter how many times I run this program. The result is same, and of course we have seen it before that the result was not same. Every time we run it, we get the different answer. So far so good. I think handling a critical section problem among threads will now be a piece of cake for you. So let me fall back to the slides. Well, let me also touch upon the attributes of a mutex. The only attribute that I have found in the documentation is its type, the type of that. Well, a mutex can be of 3 types. The first is the fast mutex. Fast mutex is the default type, and locking an already logged fast mutex will suspend the execution of the calling thread. The mutex can be error checking, and locking an already logged error checking mutex returns immediately with an error e-deadlock. The third type of mutex is recursive, and locking an already logged recursive mutex will return immediately, and a record count of lock will be kept, and it will be unlocked only when it is unlocked the same number of times as it is locked. Well, we can use these two functions, the pthread mutex attr init and pthread mutex attr set type, to initialize the mutex attribute object and set its type to something other than the default. We can see the main pages for the details. And now let me move on to the terminal and see an example code that sets the type of our mutex and shows you the behavior. Let me clear screen and let me show you the code. I think the code is in attr1.c. Well, yes. You can see I have created the mutex variable, and I have called the mutex init with default attribute. So this is a fast mutex, and over here what I'm doing is I'm double locking. In the thread function, I am trying to lock an already locked mutex, and of course if this is the default type of mutex, that is a fast mutex, it will block. Let me compile this program, attr1.c -lp thread, and let me call a.out, and you see it is locked. Let me press Ctrl plus C, and let us use the error checking mutex this time and see what is the behavior of the error checking mutex when we double lock it. And I have the example attr2.c for that. Well, over here you can see that what I'm doing is I'm creating the mutex attr underscore t type of object. I am initializing it with the default values. Then I'm calling the set type function, and the type I am mentioning this time is pthread mutex error check underscore np. And finally, this pthread mutex init function is initializing this mutex as per this attribute object. And over here, the thread function, I'm doing the same mistake, that is, I am trying to lock an already locked mutex. But this time, as per our discussion, the thread will return instead of being blocked, and this line will be printed because this is error checking mutex. And of course, I'm not doing any sort of error handling, just to keep the code simple and make you understand the concepts. attr2.c -lp thread ./a.out. So that is great. And let us fall back to the slides again. Okay, dear students, one more thing I want to touch upon is the concept and use of condition variables. Okay, so consider the famous producer-consumer problem. The producer produces information that is consumed by a consumer process. To allow producer and consumer run concurrently, we must have a buffer that can be filled by the producer and emptied by the consumer, and that buffer can be bounded or unbounded. An unbounded buffer places no practical limit on the size of the buffer. The consumer may have to wait for new items if the buffer is empty, but the producer can always produce new items. In case of a bounded buffer, it assumes a fixed size buffer, and the consumer must wait if the buffer is empty, and the producer must wait if the buffer is full. And remember, while an item is being added to or removed from the buffer is in an inconsistent state. Therefore, threads must have exclusive access to the buffer. If a consumer thread arrives while the buffer is empty, it blocks until the producer adds a new item. So let's move ahead. This is, I think, clear. We all know that in case of pipes, the kernel is responsible for the synchronization, that is implicit synchronization. Well, over here the grep is the producer process and this WC is the consumer process. The grep process writes its output into the pipe, and WC reads from the pipe. And the required synchronization is handled implicitly by the kernel. And if this producer process, that is grep, gets ahead of the consumer, that is this pipe fills up, the kernel puts this grep process to sleep when it calls write until more room is available in the pipe. Similarly, if this WC program gets ahead of the producer, that is the pipe is empty, the kernel puts the consumer to sleep when it calls read until some data is there in the pipe. So this is what is known as implicit synchronization. But being programmers, when we are accessing some shared data inside the memory, we have to do the explicit synchronization. Other than ensuring that the critical section problem is handled, we also need to ensure that some type of explicit synchronization must be performed between the producer and the consumer processes. I hope the idea is getting clear to you. Let's see this illustration over here. Let us consider a scenario in which we have 10 producer threads and we have 10 consumer threads, and this is the memory buffer pointed to by buff and is shared among all these threads. Well, each producer thread obtains a mutex lock and then accesses the buffer at the location suppose pointed to by in variable and places a number over there at that location. And Over here, the consumer thread also obtains a mutex lock and then accesses the buffer at the location pointed to by suppose out and removes that value from that location. And of course, then releases that mutex lock. So that is simple. Accessing this buffer mutually exclusively by these threads is simple. We have just used a pthread mutex t type of variable for that purpose. Well, dear students, there may be a scenario that a thread obtains a mutex lock and then discovers that it needs to wait for a condition to be true. Suppose we have a consumer thread and it wants to remove an item from an empty buffer, and this buffer is empty. It will block here, that is inside the critical section. Now a producer thread cannot place an item in this empty buffer, so a deadlock will occur. And the solution is, let the consumer thread sleep and release the lock so that the producer can produce. Similarly, consider another scenario. Suppose a producer thread wants to place an item in a buffer that is full. It will block here, that is inside the critical section. Now a consumer thread cannot consume an item from a full buffer, so a deadlock again occurs. And the solution to this is, let the producer thread sleep and release the lock so the consumer thread can consume. This is where the condition variables comes in. Solution to such problems which we have just seen in the producer consumer are condition variables. A condition variable is a synchronization construct that allows threads to suspend their execution and relinquish the processor until some condition is satisfied. The two basic operations on condition variables are signal and wait. A signal operation actually wakes up a sleeping thread waiting on that condition variable, and the wait call releases the lock, go to sleep, and later reacquire lock after that thread is waken up. So we can say that a condition variable enables a thread to sleep inside a critical section. Any lock held by the thread is automatically released when the thread is put to sleep. So a mutex is for locking and a condition variable is for waiting. Okay, so this is another illustration describing the same concept. Same producer consumer problem. We have the place item function that will be called by the producer thread, while the take item function will be called by the consumer thread. And we suppose that the buffer is empty and a consumer thread enters, get hold of the mutex and tries to call the take item function. And since the buffer is empty, so the thread calls wait on condition variable empty and gets inside this queue. And of course, before getting inside this queue, it releases that mutex variable. Now the producer process or producer thread can enter and it will call the place item function. Since it is placing an item in the empty buffer, so after that it will give a signal on the condition variable empty and it will exit. Okay, now this sleeping process or thread waiting on this condition variable empty will get hold of the lock again and execute this take item function and exit. So remember, producer thread will give a signal on the condition variable empty, while a consumer thread will give a signal on the condition variable full. And this is a scenario of a bounded buffer producer consumer problem. I hope it makes sense. Okay, dear students, the way we can create a mutex variable, similarly we can create a condition variable as well and can initialize it statically or dynamically by calling the pthread condition init function. Once we have created and initialized the condition variable, later we can use the wait and signal operations on that condition variable as per our logic. You can see the man page of wait and signal calls. for details. Okay, so well, over here just see the code of the consumer and the producer thread, a code snippet. Well, in the consumer thread, you can see if the buffer count is 0, that means the buffer is empty, the consumer thread must wait. So remember, before getting inside the buffer, the consumer thread must get hold of the mutex lock, and if the buffer is empty, it calls wait. It calls wait on this condition variable, and this second argument is this mutex variable because it has to release this mutex. It has to release this mutex and wait on this in this condition variable in a queue. So a consumer thread gets blocked in case of an empty buffer over here. Let's suppose the producer thread executes. It gets hold of the lock, and it can get hold of the lock because in the wait call, this mutex lock is released by the consumer thread. The producer thread gets hold of the lock, places the item in the buffer, and it checks that the buffer count has just incremented from 0, so it will give a signal on this condition variable empty. So this condition variable, this signal will come over here. The producer thread will exit by calling unlock. This consumer thread will now become active. This will modify the buffer, that is consume the item, and finally it will unlock and get out. I think this makes sense to you, and remember we have to use condition variable in a lot of scenarios like the one I have discussed where you cannot just make use of the mutex variable. And remember, the mutex variables are used for locking while the condition variables are used for waiting. See the main pages of these calls, and I'm leaving the solution of the producer consumer problem that I have discussed as a home task. Please do that for a better understanding. Okay, dear students, that is all for synchronization among threads. For synchronization among cooperating processes, we will use semaphores, inshallah, in some future session. I hope this session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning, and Allah Hafiz.